Hello everyone. Today we'll be tackling problem number 15, which is linear regression using gradient descent. Now, this problem is intricately related with the previous problem, which was linear regression using normal equations. I also have a video for that one, so be sure to take a look at that one first if you haven't already. This question is going to build up on that idea and is also going to solve linear regression, but with a different method, gradient descent, which is something that you're going to use pretty much no matter what type of algorithm you're using, at least in your early stages in your career. So it's worth the while just try to understand it with a simple example such as linear regression. So what we have to do here is we have to write a Python function that performs linear regression using gradient descent. We are taking two NumPy arrays, which are going to be the X or independent variables and a Y. We're also giving a value alpha, which is what we're going to refer to as the learning rate, and we're given a number of iterations. That is for how long you're going to perform your gradient descent. Afterwards, we have to return what the theta would be after you find it using this method, and we have to round it to 4 decimals. So as it's tradition, I'm going to give you some of the intuition of what's happening underneath the hood, how it is that you would solve this, and how we're going to tackle this problem. So one of the things that I find the most interesting when we're comparing the previous video with this video is that we have to think about why is this video necessary at all? What I mean by that is that in the previous video, we found what we were calling the solution to the whole gradient, to the whole linear regression problem. And what we found is that there's an optimal way to find these theta, which are the parameters of the linear regression, which came from this formula right here. It's going to be the inverse of a function x transpose times x, of a matrix x transpose times x, the inverse, and then you multiply by x transpose times y. And why is that so powerful? Because we established before that this is what minimizes the loss function. That is, in theory, no other value of theta would be better than this one. So why are we doing this whole intricate thing, this another method that I haven't even explained? Why wouldn't we just, be comfortable with this expression and forget about it? Well, there's a reason why, and it's succinctly explained here in the learn section, but let me dive a little bit deeper into that. So it is true that on pen and paper, this approach will always yield the best solution. But the thing is that in practice, it may be super hard to implement. Think about what would happen if we had a very large X matrix. So if we had a lot of features and a lot of observations, what we would have to do is we would have to invert a matrix that's going to have a very large dimension, x transpose times x is going to have a very large, it's going to be a very large square matrix. Then we also have to multiply these matrices with other matrices that are going to be quite big as well. If you have a lot of features and if you have a lot of observations, all of these matrices are going to be very big. And inverting and multiplying matrices is very costly in terms of computational terms. Now, if you're playing around with some toy data sets, you may be able to get a lot of mileage out of this formula, but if you're in a production environment with very, very big matrices, it may be too slow for you to solve the problem this way. That's where gradient descent comes in, and it's given by this formula on our right-hand side, which all it's saying is that instead of finding the optimal round from the get-go, we're going to take little steps toward the minimum of the cost function. And in doing so, as long as we keep iterating, we're going to find a solution that's going to get closer to this thing right here. It's going to be closer. It may not be the exact same solution, but it's going to be a good enough approximation with given enough time that it's going to work. So let me tell you a little bit about how that looks like. So let's say we had a function like this. When you're working with loss functions, usually they tend to be convex, so they have this kind of shape. Obviously, they may be something different depending on what type of function you're looking at and so on and so forth. But let's stay with the most basic example here. So in this function, we're going to call this red dot the minimum. And so ideally, what we're looking at is that this theta, I'm going to call theta n, which is going to be for normal. This is, if you use this theta right here, you're going to find this point. That's what we established before. But again, it may not be feasible. So there are other things that we can do. And for example, let's say we take a guess. We take a guess and we say, hey, you know what? I suppose that theta is going to be here. Now, that guess is incorrect because, as we can see, the red dot is very far away from this green point. But we don't have to stay with our initial guess. We may revisit our guess depending on where we are. So let's think about how this function is moving. On this area that's right here, that is, I'm going to make a vertical line, dotted line. To the left here, the derivative, or rather the gradient of this loss function is going to be negative. Why? Because the loss function, this thing, which I'm calling j, is going down if you keep moving in this direction. So if you're here, if you're here, if you're here, it doesn't matter. You're moving in a negative direction. That's because you're moving closer to this red point. However, if you're on the other side of the red point, the opposite happens. The gradient is going to be positive. And so if you're, for example, in this other point here, this yellow point, if you increase the theta by a small amount, you're going to move towards here. And here you're going to move towards here. So what we would like to do is we would like to tell our function, hey, we made a guess. We want to revisit our guess so we move closer towards the theta. And the way you do that is by using your gradient, this thing right here, what we established. So whenever you're moving in one or the other direction, so if you're moving downwards, if you're in this point and your derivative is negative, what you want to do is you want to get a higher theta because your theta is too small in this area. So in this area, we would like the theta to increase. That may not be too descriptive. Let me call it like this. In this area, we want theta to increase. In this other area, we want the opposite. If theta increases, we'll be moving further and further away from the minimum. So here what we want is the theta to go down. And as you can see, the movement that you have in both of these areas goes against the gradient. That is, if the gradient is positive, you want to lower your theta. If the gradient is negative, you want to increase your theta. So what we would like to do is we would like to move in the opposite direction of the theta, of the gradient. And that's going to move us closer to the optimal theta. That's why it's called a gradient descent, because we're descending towards the gradient and we're moving in an opposite direction to it. Now, there's a more general formula for this thing, which I'm going to write down in a minute. But the main idea is that if you have a theta right here, you're going to revisit it by saying, I'm grabbing whatever theta I had, I'm subtracting the gradient, because as we saw, if the gradient is negative, I want a bigger theta. And if the gradient is positive, I want a smaller theta. And that's going to be kind of the gist of it. And why are we moving in this magnitude? Well, because that's as much as we can know from this function. So the gradient is going to tell us how we're moving, and this magnitude is going to be taken as a proportion of the gradient. Now, this looks fine and dandy, but let's think about it a little bit deeper. So if in every single iteration you're going to move in this way, it may be that this magnitude is either too big or too small. There must be a way to, obviously the gradient, the magnitude of the gradient is going to change depending on where you are in the function. But even then, you may want to adjust this size of the step that you want to take. And that's why we have what we call the learning rate. So the learning rate is going to tell us the size of the step, how big we're going to move, and how big the step that we're taking towards the minimum is going to be. And this thing here, the gradient, it's also going to help with the magnitude, but we can interpret it as the direction that we're going. Again, you're always moving in this type of function against the gradient. So that's why if this thing is positive, you want to move backwards. If this thing is negative, you want to move forward. So with that in mind, that's where the formula comes from. That's why we're using gradient descent, and that's how it works. Now, the way you implement this thing is that you do it multiple times. There might be other stopping criteria that we could explore in different videos, but for now, just think about this as you define a set amount of times that you're going to perform this update, and then you just do it. Okay, so that's all fine and dandy, but let's talk a little bit more about this alpha, this learning rate. Because in the function, in the question itself, in the question statement, they mention something about the size of the step in this learning section. So why is it so relevant? Or rather, what would happen depending on the theta, on the alpha? Why is it important? So let's think about it intuitively. If we pick a very small alpha, so for example, alpha is very close to 0, well, what would happen is that we would have to take a lot of steps to get towards this red point. So we would move like this, we'll move like this, we'll move like this, like this. I'm trying to make it very small so you can get the idea that although we're moving in the right direction, the way we're moving is very slow. And it may take forever to get to this point. So having a very small alpha is not efficient because you're going to waste a lot of time getting towards the minimum. It's not that bad in the sense that you would eventually get there, but it may just take too much computing power for you to get there. And remember, the whole reason why we're thinking about gradient descent is because we know that inverting all of these matrices may be too computationally expensive. Let's think now about what would happen if we had a very, very large alpha. And I'm going to put this, these are supposed to be greater than signs. So if we took a very large alpha, the risk we run is that we may overshoot. So let's say we start here and then we take a very big step, we may end up here. So now we have another problem. We overshoot. Okay. Oh, so I'm over here. I know that I need to make my theta smaller. So let me make it smaller. Oops. I also overshoot again. Okay, let me try again. Oops, I overshoot again. And again. And again. It doesn't have to be as radical and increasing as I'm doing it. This is just to illustrate a point. But the whole gist of it is that if you have a very large learning rate, you may never reach the minimum. This whole thing may diverge because you're just jumping around the whole area because it's too hard to find. So that's why we are interested in finding a precise learning rate. That is what we end up tuning when we're implementing an actual algorithm. That's one of the hyperparameters. That's out of the scope of this problem, but just so you keep in mind, because this kind of thing will show up no matter what type of problem or algorithm you're implementing. So with all of that in mind, how do we solve the gradient descent for linear regression? Well, as I said, we're going to have to implement this formula from scratch. Well, not entirely from scratch because we're using NumPy, but this is the formula we have to implement. And this, you may be wondering, why is this different from what is given here in the learn section? They are entirely the same. The main difference is that this thing is looking at each element by itself. This thing is looking at the whole matrix instead of just one element by itself. And I'm going to talk a little bit more about why this whole thing will happen. Okay, so anyway, if we have a theta, we can implement this. This is given by the code. Now we have to find this gradient. And we already did that in the previous video, so I'm going to move a little bit faster here. But in case you need a little refresher, the cost function for the linear regression is going to be this thing, theta times x minus y transpose times theta x minus y. And if you take the gradient with respect to theta, I'm going to skip a lot of steps because, well, this is divided by 2. Oops, divided by 2. We're going to omit that. And if we take the gradient with respect to theta, the expression we end up with is x transpose x theta minus x transpose y. Again, if you're kind of puzzled by this, go check the other video. I take a lot of time deriving this thing. And we can write it more nicely as this. We factor out the x transpose. Oops. Yeah, we factor out the x transpose. And then we have this other thing here. And that's the whole solution. So this is what we're going to plug in here. And this is what we end up coding into the machine learning problem. This is basically the whole thing that we need. One last thing that I just noticed that I forgot to mention before is that we have to divide by m. This is kind of a normalization term which I just omitted. M is going to be the number of training examples. So apologies for omitting that until now, but this is pretty much just a correction. The whole other intuition and idea of what I just mentioned is the gist of it, and it's exactly what you need to do when you're coding it up. So now that we understand where the gradient descent is coming from, why it works, and how it applies to linear regression, let's go dive into the code. Great. So now that we're back here, remember what we want to implement is this gradient descent approach, and we already found the gradient of the loss function. So let's dive into it. The status code here is pretty nice because we already have some legwork started. We already initialized theta to a number. When you're implementing gradient descent, you want to initialize theta to one number. Some people just do a random matrix. Some people go with zeros. Either is fine. There's certain situations in which you will prefer one or the other, but for now, let's just stick with the zeros. And we're going to have the shape of the x function. So how is the gradient descent going to work? So we first have to define the number of iterations, or rather define the loop that we're going to do, because we're given the number of iterations we're going to take. So we're going to call for underscore in range iterations. If you haven't seen this kind of for loop before, let me just tell you that whenever you don't need a variable to keep track of which iteration you're in, you can just do this. And so it's just going to execute the for loop for the number of times you said, but you're not generating a new variable for each loop. And that's going to be helpful for saving memory. It's also good practice to indicate to someone who's reading it, the iteration you're in doesn't really matter, at least to get the number, because the way you're going to know that you're updating your variables is going to come from somewhere else. But in any case, we already have that. Let us define our predictions. So these predictions is going to be x at theta. So what I mean by the predictions is the multiplication of your parameters with your input. Remember that that's what's going to give you the predictions of the y vector in your model. And if you're kind of confused about why I'm using at to indicate multiplications, let me say that for 2D matrices and for 1D matrices, that is 1 or 2 dimensions, it's the same as doing point dot. This thing is only different if you're working with 3D matrices and up, but for this problem, it's kind of the same. You can do it with the point dot or with a at. Okay, so now that we have that, let's get the errors, which is going to be the predictions minus I. Now, remember that it's a good practice to reshape this to indicate that it's a vector. Because okay, this is given as an array, okay. And this is going to be what's inside of the parentheses in our expression. Just as a reminder, the expression that we got out of the way was x transpose x theta minus y. So with all of that, we already have this. This is what we're calling the errors. Okay, so that out of the way, what we have to do now is we have to multiply these errors by the x transpose. So remember, we can transpose a matrix by just putting the method point t. We're going to multiply it with the errors, and we're going to divide by m, which is the thing that I told you helps us a correction for the size of the matrix. Afterwards, we have to plug this into our expression for gradient descent, which is theta equals theta minus alpha times this gradient, which is what we called the updates here. And so in this case, our theta, we're going to do minus equal. That is in order to avoid writing equal theta again, because we already know that we're just going to subtract this thing from that. And we're going to do alpha times updates. And with that in mind, we are going to have the loop of one iteration of gradient descent. And as I said before, this is going to keep going, keep going, keep going. Now we have to make sure to round our result. So all of this is already giving us our theta just to comply with the requirements for the problem. Let us round that. So we're going to call np.round to the rounding method, theta. We're going to flatten it. That is so it has the shape of a flattened array. That's going to be kind of like a vector, a flat vector of one row. And we're going to round this to 4 decimals, which is what the question is asking for. And with that in mind, that's all of the code. We should run it and it should work just as expected. So that's great. As you can see, we got the same output and it's as expected before. Now, this is a great problem, in my opinion, because gradient descent is a very useful technique. You should really keep it in your arsenal and be familiar with it. Linear regression is also a very straightforward algorithm, so it's fantastic for practice. So I hope you learned something out of this video, and I hope you can now feel more confident implementing gradient descent in your future projects. Thank you so much for your attention, and I hope to see you in the next video.